Thank you for USBI and the organizers for this invitation. I'm very honored to be here presenting. Um, my presentation today, it's going to be showing and sharing with everyone the result of 4 to 5 years of work that was done on applying biochar to a sugarcane field and looking at year after year the results on harvest and sugar yield. So the way I'm going to organize my presentation today, I'm going to tell you a little bit about sugarcane production worldwide and also in Louisiana, the state where I reside. What's the problem statement for this specific feedstock? Um, how I went ahead and set up the field, how it was harvested. Then I'll go a little bit into the characterization of the biochar that I produced in my own laboratory at USDA. Then show you a little bit about the results of this field study, a little bit about conclusions and what's next and what the implications that this data can give to the sugarcane industry and to the biochar manufacturing as a whole. And then finally, if I have time, I would like to share a few videos with you of a recent trial. We just started a larger trial. All right, so sugarcane around the world. As you all know, sugarcane is native to tropical and semi-tropical climates, and it's grown in more than 90 countries worldwide. We here in Louisiana, I believe, we're the most northern growing region in the world for sugarcane, which gives specific challenges. And we produce about 190,000 hectares, and we generate about 15 million tons of sugarcane a year. And that generates about 1.8 million tons of raw sugar, give and take. Sugarcane, as I said, is the world's largest crop by production quantity, with 64 million acres dedicated to it and an annual production of 1.83 billion tons. And this generates worldwide 280 million metric tons of biomass residues. And that's sugarcane bagasse and field residues. We're not number one. Number one is Brazil, and the majority of their sugar production actually goes for ethanol production, but they do produce sugarcane for both those applications. India, China, Thailand, Pakistan follow Brazil, and US is number 10th in the world. And sugarcane production counts about 80%, with with the remaining 20% being produced from sugar beet, and those are generally in cold climates. So what's the problem, or can we say what's the opportunity here? What are the processing residues of sugarcane production? Is it a disposal problem, or is it an economic benefit? So the production of sugarcane generates sugarcane bagasse, generates fly ash from burning that bagasse to produce energy to run the mills, and it generates leafy residue at the field. So those are the three major outcomes as far as residue or biomass that you can generate from handling sugarcane. At the factory, you generate the bagasse, and that's about, this is a Louisiana statistics, 4 to 5 million tons. And about 80% of that is used as fuel for running the mills. 20% is surplus. That's the surplus that we can use for other applications. The burning of that sugarcane bagasse generates fly ash, and that's about 50 to 100,000 tons. And the leafy residue is generated at the field, and that's about an estimated 6 tons per acre. Given that we have about 450, give and take, thousand acres in Louisiana, we generate about 2.5 million tons of that residue in Louisiana. So this is a liability to growers and processors, because both those residues have high moisture, so they are prone to decomposition and microbial degradation. But the good thing about these residues, specifically for the sugarcane bagasse, is that they are co-located with harvesting or processing facilities. So there's no transportation costs. They're right there at the mill. We want to add value by converting these residues locally to biochars, and we do so, as you all know, via thermochemical pyrolysis. And then we want to bring them back to fertilize those same soils where they came from. So we believe this can give profits to the growers and the factories and helps protect the environment and public health, because storing this bagasse outside in big bagasse piles is actually an environmental problem. So we did a four-year field study with a single biochar application. We applied it 1 year and we measure harvesting for 4 years in a row with one single biochar application. That's important to know. Our feedstock was either the sugarcane leaf residue or the sugarcane bagasse. I made these biochars in my own laboratory, and the furnace you see down below, there was a little steel basket that was produced to fit the retort. It's a 22-liter retort, and that furnace ran nonstop for probably 6 months for me to generate enough biochar to do a field study. The soil we use is a common soil used here in Houma, which is about 100 kilometers southwest of New Orleans, where we have sister laboratory facilities. The field was applied in single seed cane applications in furrow before we covered it with soil. The fertilizer practices were as normal commercial practices, as well as the pest management. The biochar again was made from either bagasse or leaf residue at either two rates, 800 or 1600 kilograms per hectare. And then we also applied fly ash from the mill at those two rates. And we judge the application rates are high or low on those two elements based on their mineral content. So we did either single applications or in combination at either low level 1 or 2. Then every year we harvest millable stalks. They were all counted, and then we estimated per hectare or per acre. We estimated the amount of stalks, and that was used as a statistics for our measurements. We cut random 10 stalks per plot. We weighed them, crushed them, we extracted the juice, and we analyzed. And I'll show pictures of that coming up. We calculated the yields using the stalk counts, the fresh weight of the stalk, and then the sugar yield in terms of kilograms of sugar per ton of cane. Here's AMI weighing the biochar. It's dirty business. Once we were done, we didn't look as clean as when we started. Of course, the day we decided to plant, we had a huge rain event, but we rushed it and we were able to complete it before we got soaking wet. Here's the field. This is a standard field. And there's about 3 meter single row treatments that's separated by a buffer of 0.6 meters. We did 15 different treatments depending on single, high-low combinations and the 3 types of feedstock biochars. And we also used controls. And here you see the field as we were applying. So we applied the seed cane right here, and then we applied the biochar on top of it. And in the end, we had this row cover tractor pulled that covered each one of the rows after biochar and the seed application. And then we had growth checks, and we would go in every month and count number of stalks up to all the way up to harvesting. This is just your traditional harvesting equipment, but on the bottom left, you see all our 10 stalks all wrapped and ready to go for analysis. This is our sister laboratory facilities where we process the stalks. We have here a cane shredder that shreds the cane, and this is how we extract the juice. So this cane shredder here shreds the cane. Basically, it opens up the cells without getting the sugar juice to come out. It just opens the cells, and then they get pressed in this presser, sugar presser, and it's a known amount of shredded cane. It's 1 kilo exactly. So then we extract the juice here, and that's how we do the measurements. And this is what's left, the basically dried sugar cane once the sugar is pressed. Okay, well, on to some results. We did some scanning electromicrographs of both the sugarcane bagasse biochar and the leaf residue biochar. And here's the leaf residue biochar. As you can see, because the cell structure is already there, part of this cellular material. So these structures developed from the get-go, and the pyrolysis process of making the biochar enhanced this types of structure that we observe that show that there's a high porosity associated with this types of materials. Here's the sugarcane bagasse raw on top, and then once you get charred, you see it at different magnification rates. You see the microstructure of these materials develop. For the fly ash is basically the result of the combustion of sugarcane bagasse. So there's not a lot of structure here. It's very poor in carbon, but it still has some carbon left. So you almost see about the same original structures than you saw from the bagasse and the leaf residue, but much less development of porosity. Okay, now on to some physical chemical properties of these materials. Here on the left, you see we start with leaf residue, the raw material, and then the BCs, the respective biochar. The yield values for the biochar for the leaf residue are about 41% and the bagasse 35%. The surface areas are 22 square meters per gram for the leaf residue biochar versus 148 for the bagasse. And the fly ash surface areas we expected is negligent. pH, both biochars were slightly alkaline to more alkaline for the leaf residue due to the content of minerals. And these are very, very light materials. The density is very low, particularly on the leaf residue biochar, which can sometimes present challenges when spreading it in the field. But of course, this compared to the density for the soil. Carbon content was about 45% and 59% for the bagasse biochar. Here we look at approximate analysis, looking at both the volatile content, the fixed carbon content, and the ash content of these materials. And comparing leaf residue with bagasse, you see that as you go through the process of going from the raw material to the biochar, you significantly decrease the volatile material because it's going to volatilize, obviously, and you are increasing the fixed carbon in your biochar. You're going from almost 20% to 60% in the leaf residue and bagasse biochars. Ash, accordingly, also goes up naturally because you're reducing the carbon fraction, so you're increasing biologic, you're increasing the amount of ash in those materials. So it's about 29% and 26%. So what happens with the biochar manufacturing, as you all know, you have a carbonization. So they have these aromatic structures that are growing and developing through polymerization reactions, and that leads to carbon enrichment and development and porosity as you volatilize your volatile matter. Now, looking at the mineral contents, we looked at the major ones on the leaf residue and the bagasse biochars, and we compared them also to the fly ash. So you see that from here, biochar and the fly ash, they both contribute nutrients to the sugarcane crop, mainly phosphorus, calcium, and potassium. The original mineral concentrations were higher in the leaf residue, and we kind of knew that. The concentration from the raw material to the biochar increased about 2.8-fold for the leaf residue, where it went from 4.5 to 7-fold for the bagasse biochar. The fly ash content in calcium and manganese was lower, but it was higher in iron. Now, on to our statistic analysis. So we looked at all these combinations. We looked at single treatments, low and high amounts, and we looked at combined treatments. So we looked at not only the effect of the treatment on the cane yield and the sugar per ton of bagasse, but we also looked at the year. Every year we harvested, and we understand that there's very important changes that happen year to year just because of weather events and other things and rainfall and whatnot. So we knew that the year would have a significant effect, and we can see that here. But most importantly, besides the year, the treatment has a significant effect. So we look on the left here, we see cane yield in tons per hectare, right? And you see the control here at the lowest. We found 102.5 tons per hectare cane yield, and that was the lowest one. Every single treatment, whether it included biochar from bagasse, biochar from leaf residue, all combinations thereof, had higher cane yield than the control. That line just shows the combinations that were significantly different from the control. Anything below the line was not significantly different from the control. On the right side of this table, you see the same thing, but this is TRS, which basically it's the terminology, the industry terminology for sugar content per ton of cane, which is also important. So they were both significant the same way. There was an year effect, but there was also a treatment effect. So anything above that line is significantly different from the control. And interesting enough, we see different groups playing a different role on the sugar content that played a role on the cane yield. Looking at sugar per hectare, and how do we get sugar per hectare? Basically by multiplying those two other values. You get cane yield, you get sugar per ton, and then when you multiply them both, you basically get the value that you really want. How much sugar am I getting per hectare of cane? And this is what this data shows. So we're looking at subgroups now. We wanted to understand the difference between the single treatments versus the combined treatments where we had bagasse biochar with fly ash. So we see here that here is no longer significant effect, but treatment still is. Control still had the lowest sugar production per hectare, both on the combined treatments and on the single treatments. And on the left for the combined treatments, bagasse had the highest sugar per hectare versus on the single treatments, interesting enough, the leaf residue at the lower level had the highest sugar per hectare and significantly different and much higher than the controls. Then we looked at low versus high application rate treatment. So basically the lower application rate versus the higher. And interesting enough, if you look at the low application, you see that the year again is not significant, but our treatment is significant. And the control had the lowest amount for sugar produced per hectare, and the leaf residue had the highest amount. When you look at the higher application treatments, then the bagasse was the one that came above, with above all of them. But all these combinations and all these either lower or higher treatments were always higher for sugar production per hectare than the control, and significantly higher. So now, when we combine all these statistics together, and just for you to understand, what was more important in the study to observe was that we looked at first, second, third, and fourth year separately, and then we combine all years, or we average them all together. And this is what we find. If you look at the control, means that this is sugar produced per hectare on the field that had no biochar treatment, no fly ash treatment, nothing. It only had the biochar, and it only had the regular fertilizer treatment. So we found out in the first year that we generated 11,000 kilograms per hectare. In the second year, in the third year, and the fourth year, that amount went down. This is expected because we do the planting and then you have the first, second, and third stubble. So your yield is supposed to go down. That's why every 4 to 5 years you have to go back and replant. So this is expected. Now, when we look at the average per treatment for each year, this is average across all treatments, we see a totally different statistics. We see not only that we have a little bit higher sugar per hectare, but that these values, instead of going down, not like I expected to go down, they actually do slightly go up. So if you calculate the percent increase from the control, it's not very significant in the first year. So if you only look at the first year, you think, well, the biochar didn't really make much difference, or the treatment didn't make much difference. But if you look over second year, third, and fourth year, then the differences are significant, because instead of going down in sugar production per hectare, then you go up. So the cumulative effects are significant. And down below here, I just show, just for you to understand that due to rainfall events and whatnot, and even high and low temperatures across the whole harvesting year, all the months, we see that the differences are significant enough that sometimes that's why year by year we have different significant differences that are just affected by environmental conditions. So here are the overall trends. Here we're looking at the treatment, the control, the leaf residue at value level 1, 2, the gas 1, 2, and fly ash 1, 2. So we have number of millable stalks per hectare. We have sugarcane yield in tons per hectare. We have sugar in kilograms per ton. And then finally, we have the sugar yield in kilograms per hectare. So let's focus on this. Again, the control had the lowest amount, and all the treatments were higher than the control at these differences. And the latter showed significant differences where they are found. So basically, we find that sugarcane yield increased following biochar and fly ash additions at the two rates that were used. Both the sugar yield and the sugar per hectare also increased for all treatments used as compared to no treatment. You see here when you compare to the leaf residue applied, leaf residue biochar applied at the lowest level, that we had stalk count increase, we had cane increase, and sugar yield increase. And this is the amount, an increase by almost 8,600 stalks per hectare, 26 tons per hectare, and for the cane yield, and 3,100 kilograms per hectare of sugar. So if we now do a cumulative data, what does that mean? Because we had a single application for 4 years. If you do the cumulative data and add all those 4 years in a row, add all the production of sugar, all the production of cane, then this is how we get these numbers. So we're looking at, again, control, the different biochars, and we have the sugarcane yield in terms of cane, the sugar yield in terms of sugar per cane, per hectare. And then if I assume a domestic sugar cost or price of 0.572 cents or dollar per kilogram of sugar, I was able to calculate this value. So I was able to basically calculate how much more money I made from that extra sugar from doing this treatment. So I have the value based on the value of sugar for the control. And then each one of these additional treatments has additional value. So this is the difference from the control. So for example, for leaf residue biochar, I had a difference from the control of $7,150 over the 4 years cumulative data. So as you can see, this was the highest number, but all treatments generated surplus because of the extra sugar per hectare generated. So in summary, biochar improves soil structure, contributes nutrients to the field and the sugarcane crop, and builds soil organic carbon and increases the pH of the soil. This can be seen as a sustainable means to sequester the carbon by increasing the recalcitrant pool of carbon in the soil. So when we added biochar to the soil, we consistently saw improvements in both the total sugar as well cane yield when compared to no biochar or no fly ash additions. Single application, this was a single application of either biochar and or fly ash, resulted in increased sugarcane per hectare yields. And this was over the 4 years of this study, as opposed to expected decreased yields observed from the controls. So in general, the application of biochar from leaf residue increased the stalk count, cane yield, and sugarcane yield by these amounts on those 4 years average. The cumulative profits and increased commodity value over the several crop years can be foreseen, and this was only with a single application of biochar. The best outcome we found for the study, as I showed, was generated estimated sugar profits up to an additional $7,000 per hectare, and this was found for the leaf residue biochar over no treatment. So we envision research benefits to the sugarcane industry. We want not only for energy to be produced, but biochar to generate yields and profits. And we believe that this is a sustainable soil management approach, adding carbon to soil and reducing the fertilizer costs. And also handling those massive amounts of bagasse that are generated each year that are not used. This is also very important to get information for assessing the sugar industry's role in the alternative energy market. So switching gears a little bit, hopefully I still have time. I'm continuing on this study, and what we're doing right now, we're collaborating. I've been collaborating with American Biocarbon for about 5 years or more. They currently have demonstration plant. They've had that for several years now. And that demonstration plant is a small plant that is right next, sited where Sugarcane, Cora, Texas mill is, located in White Castle, Louisiana. And that demonstration plant produces biochar, and it's a small enough that can prove test efficacy of production processes, feedstocks, and products. So they can test different batches of bagasse, different batches of leaf residue, whatnot, and do so at a smaller scale. So this one is rated at about 2 tons per hour of pellets and a 0.5, half a ton of biochar per hour. They are planning to develop a full commercial scale starting in the next few quarters in 2021. And that one plant, the commercial plant, will have a design capacity of 100,000 tons of pellets per year and 46,000 tons of per year of biochar. The facility will utilize 100% of the excess bagasse that is produced at the Cora, Texas facility, and will consume both the aged bagasse that they have on site piled up, as well as residue, leafy residue from the field. They estimate about a year or so for commercial operation. All right, now hopefully this will work. Together with their collaboration, they have a lot of biochar that they have generated over the last years on site, and way more than I can ever generate in the lab. So they supply this, graciously supply this biochar for our next field test. And the folks at Cora, Texas also, and at the farm, graciously supply their time and labor to help us with this big project. We're going to do 2 different soil types, and we're applying in one of them. It's both relatively poor soil and a clay soil, and we're applying about 20 acres of each. One is 20 acres, one is 12 acres, and we're applying biochar from bagasse to these fields. And so we have biochar and also control plots. So let me show you a little bit of the video. Wonder how we can make this a little larger, I'm not sure. I'm not sure if we can make this a little larger, but if anyone can see. This was done in September, this past September, on a very, very hot and humid day. This is a look at the biochar, and this is my very, very rudimentary moisture measuring technique at the field. Here, they're loading the biochar onto this spreader loader. They're using a tractor. We're loading the biochar. And then I'm going to show you how it's done. All right, so this is the tractor with an opening tool. It just basically opens the roll so they're ready to get the biochar and the seed cane applied to it. So they were prepping the field for the biochar. Here, the biochar application. That's the tractor driving the biochar, and we made the calculation based on weight and density and whatnot, so that we applied 1 ton per acre biochar. That was the calculation, and that's how Biochar was delivered. And it was pretty effective. The Biochar was not completely dry, which was good. It facilitated the application of Biochar then. This is a side view of the application of Biochar. So we alternated rows. It applied 3 rows at a time, and we alternated. We had about 20 rows, and we alternated Biochar, no Biochar, Biochar, no Biochar. So we're going to have several replications of this. And then here you have a little view of the rows after Biochar application. So we applied the Biochar first, and this is just for you to see how they harvest the seed cane. This is called the soldier harvester, and it does a single row at a time, and it harvests 1 row at a time of cane, and it kind of drops them down, and then there's another piece of equipment that comes back and collects the cane that's dropping on the ground. And this is again they're going to be using seed in the field, and this is done about every 4 to 5 years. All right, here, after Biochar application, opening the rows, Biochar application, then this is commonly done manually, can also be done with a tractor, automatic, but most typically it's done manually. So then they're dropping seed cane, and they do a really, really good job dropping the cane. They drop the cane on the rows, following the Biochar application. And this is called a tractor with a closing tool. It physically comes back and closes every single one of those rows. So the Biochar and the seed cane is contained within the row and at about the depth of about 2 to 3 inches. This is a front view of the tractor with a closing tool, closing up the rows. And now the cane is ready to go. It's set. It's sitting there since September. And this cane is going to be kind of growing a little bit, but going through the winter months is going to start growing in the spring, and we will be harvesting it in October through December next year. So with this, I thank you for your time, and I welcome any questions you might have.
Thank you, Dr. Lima. I believe Kim has gathered some questions up for you. We'll just take a couple minutes to do some questions and answers. And if we don't get to those, we'll send those to you so you can answer them and get back to everyone.
All right.
Kim, do you have the questions?
I do. Very exciting and interesting presentation. Thank you, Dr. Lima.
Thank you.
Yes, we do have a number of questions here. Let me start with the first one. Have you published your work? And if so, where has it been published?
It's in the process. I'm writing the paper as we speak, and I actually had hoped to have it published by now, but it's in the works, and it will be out probably within the next few months, hopefully, depending on the review process. But it will be published. I mean, the paper is basically done. You just have to go through the review. Journal, probably in the International Sugar Journal, which is a good. It's a good journal for the the sugarcane processing folks, but I'll let everyone know. I thought it was a good. It's a good applicable journal for this type of research, and it's both basic and applied science. So given that this is such an applicable commercial setting situation, that I thought there was probably the most fitted journal for that.
Thank you. I would imagine that people could just Google your name and look for publications in a month or so, and they would be able to probably find that reference to that publication.
Correct. Yeah, and the publication will definitely delve into way more information than I was able to give today.
Okay, thank you.
Yeah.
The next question is from David Scott. Is there any concern that the increase in nutrients to the soil will degrade water quality in rain runoff?
I don't think so. I have not done those tests, but I would imagine not, because you really, if you think that I'm returning the nutrients that I took back, so if anything, I'm doing the soil a favor. The soil is being depleted of nutrients every time there's a harvesting. So we're just basically bringing the nutrients back in a better fashion, adding soil carbon to the mix as well. So understanding that the whole growing of the sugarcane and harvesting and taking that material out with depleting the soil, so bringing it back as the biochar version, I don't think that deplete or that leads to those consequences, because we're just really bringing back those nutrients that we took out.
Next question, Eli from Eli Fishpaw. What fertilizer did you add to the sugarcane?
It's the traditional, I would have to get back with you precisely, but it's best management or best practices that they use. It's what the sugar industry recommends for needs for the sugarcane as far as phosphorus, potassium, and nitrogen. Particularly nitrogen. Phosphorus and potassium are not so required, but they're part of best management practices. But nitrogen is, I had a slide there about how much it was added. So it's exactly based on industrial practices.
Thank you. From David, Dr. Lima, these are impressive results. I would love to know the cane producers' reaction to your data. Thank you.
They're all very excited, and that's why we're doing this field study, and I have full support of not only the mill personnel, the farm that is graciously giving not only time, but all their people, their labor. You saw all the people working to do this. This was a hard day at the field, applying the biochar. American Biocarbon is helping supply the biochar. So we have a whole bunch of people helping out to do this long-term study. So you just have to wait 5 years to hear from me because we have to do the 5-year study to do the long-term study and understand what happens year after year, if there's any improvements.
Thank you. This is for me. What are the largest remaining challenges to getting the sugarcane industry to adopting biochar as a standard practice, either in the US or outside?
I think proof is in the pudding. They want to see results, number one, of course. They want to see it work commercially. So what was done so far was semi-commercial, was an a sugarcane farm, but it was still with biochar that I made in my own laboratory. This is going to be a commercial study done at a farm with commercial produced biochar. But at the end of the day, I think they just want to understand that there's return on investment, that how much is the biochar going to cost and are they going to see those benefits? So the investment to pay for the biochar, will they see that in return for increased sugarcane yields and increased sugar yields? They want to make sure that the cost is worth. And in this situation, you need to understand that we show them that there's benefits, but they have to wait, even though there's a single application. So there's the time lag of understanding that there's benefits, but they don't happen immediately. They have to invest on the biochar first, apply it, and maybe wait over the period of 4 years to realize the benefits.
So does this is again for me. So does that mean that they're not going to have to replant after 4 years? Do you know how long they could go without having to replant?
Good question. In hindsight, I wish I was able to continue. I was only able to do a 4-year harvesting because the field that I was graciously given to use, some other scientists needed to use it, so I couldn't continue. And at the time, I thought I had enough data. If I had continued, it would have been nice. I'm not sure if that would have plateaued. And at one point in time, we would no longer see significant benefits from the treatment. At which point you have to go ahead and replant. There's no doubt that they'll have to replant. It's just what we're trying to tell them is maybe with this biochar application, they can extend their replanting. So instead of replanting every 4 years, they maybe can replant every 7 years. And they're significant. And I did not incorporate those costs or those profits into my calculations, right? So if they go from a 4-year planting cycle to a 7-year planting cycle, those are huge savings because it does cost to plant. And if we take that into account over the long haul, that will make the biochar cost and application much more doable.
Thank
So
you.
we hope to do longer term studies. So when I say 5, as long as they tolerate me around, I'll try to do and continue this study as long as I can.
Okay. And those crops that were planted they're continuing on, they're not replanting them, or are they? The ones that
every year so you mean the one study we started right now in September?
In the 4th year, after the 4th year, are they replanting now that crop or not?
We just started, yes.
Okay.
So the crop we just started this year, I'm not going to get them replanted. I'm hoping to get probably at least 5 years. And each year I'm going to be looking at yields. I'm going to be each year I'm going to be doing the data analysis and figuring out what the data is telling me. So if the results are positive, there's no reason why we should stop it. So I'll probably continue 4th, 5th, 6th year. So and this is of their interest as well. So I would imagine that we would continue beyond the 5 years.
Excellent.
Especially if the results are encouraging with the biochar application.
Thank you. This is from Taki Raza. What is the best temperature for the production of biochar from bagasse? As I produced biochar at 450 C for 6 in muffle furnace, but here, what is the best? Let's see, that was cut off. But here she used 650 C. Kindly, can you suggest me the best temperature for the production of biochar by muffle furnace from bagasse?
It's hard to say because it depends on the application. It depends on the soil. It depends on the crop you're growing. I did it at 650, but honestly, this biochar we're using was produced at a lower temperature. So I would say 450 to 650 would be okay. I have not, because in this previous study that I reported here, I only produced at 1 temperature. It's hard for me to derive and saying if I use the lower temperature, if I use higher temperature, what would the significant changes be? And would there be any significant changes? I only used 1 temperature, so it's hard for me to say what I didn't observe. But I would say more important than temperature would be probably your relationships of your soil dynamics with your biochar, what soil do you have and what crop you have growing, and also your feedstock for making the biochar. So I'm not sure if 450 wouldn't be good. I think 450, anywhere between 450 and 650 would be okay. I can't recommend any other temperature because for my study, I don't have a comparison. I use 650.
Mm-hmm.
So I don't know if lower temperature would have gotten better results.
This is from Luis Ramos. Nice presentation. Are there differences in biochar yield on a dry basis between cane bagasse and cane leaves?
Say that again. So if there's any difference between
biochar yield on a dry basis between cane bagasse and cane leaves?
Yes. We got actually slightly higher yield with leaf residue biochar. It was a 5% difference. Again, that depends on your temperature pyrolysis and residence time in the furnace and whatnot, and even the quality of the bagasse and the quality of leaf residue. The leaf residue I used was actual leaf residue, but it depends on if it's contaminated with other types of materials. But yields generally are between low 30s to low 40s. Big determinant of the yield is temperature. The higher the temperature, the lower the yield, and the higher the residence time, also the lower the yield. But it pretty much, for those two materials, it ranges between low 30s and low 40s. On a dry basis also.
Thank you very much, Dr. Lima. For the rest of you who asked questions, there were a lot of questions for Dr. Lima. Don't worry, we are going to be publishing and getting back to people on the answers to the other questions. It may take a week or so, but we will be answering all the questions. Dr. Lima will be. Thank you so much, Dr. Lima. Really appreciate your presentation.
Thank you.
Thank you, Dr. Lima.